There you go. So this is joint work with some of my amazing students in my lab and postdocs. I'm going to start with something. Diffusion. When you think of diffusion, what do you think of? You think of maybe throwing a stone in a pond. You think of maybe putting a drop of dye in a liquid, and things disperse. They diffuse, right? When you cook, after that, you want to put in an incense. That also diffuses, right? It changes things. The whole idea of diffusion is you start at some point in a very informative setting because you put this drop of liquid at a point, and eventually it just diffuses and everything looks the same at some point, right? Nature just balances out. Could we do that with images that we have? Take images that we really have and we want to generate new images, but we diffuse them to nothing, but the model we learn to get them back to something can be then used outside without the training data, all right? So basically, you want to transform informative data to diffuse states, and then we're going to learn a machine learning model. Now, Cantor system theory, how can we do this? We're going to take inspiration again from the mathematics of diffusion. We, physicists, can actually write equations for forward diffusion. In nature, there's only one way. You always go from high energy to low energy states, high entropy to low entropy states, right? So diffusion is actually what's called a process in time. So it's actually a differential equation, but it also has noise in it. So there's two parts. There's the drift and the diffusion. And that leads to a stochastic differential equation. What we want to do is not only do we want to follow this path, we also want to reverse this path. Can we actually do that? You can do that because of the following reason. Diffusion in nature is stochastic. However, the equations that I showed you before actually have a solution to the probability model. And the probability model tells you at any point in space and time how much of that blue dye is there. But going from a particular intensity of the dye to another intensity of the dye is a trajectory in time. I need to go on the right trajectory because there are many that are possible. The distribution actually tells me how to do that. So a reverse diffusion can be written actually, starting with this forward time model, by sort of reverting that time model, but actually also using the knowledge of the distributions of the data. Now, this is all a lot of math. The key idea is that we can revert. This is all written in continuous time. We can do this in discrete time. So this leads us to what we do in practice, discrete time diffusion models. All right? So in your head, you start with an image at time t equals 0, x 0. You're going to noise it. That's the forward process. You're not just going to noise it in one step. You're going to noise it a little at a time. It makes it easier to do things. And you stop at some point. So all the math there is telling you is you're going to reduce the intensity of the signal and increase the intensity of the noise as you go through. All right? I want to reverse this. Well, noise occurs naturally, and you can never learn the correct exact noise that you added. But if you have an idea of the process, you can actually learn the noise. All right? So this seems funny, but what we want to do is, in a training of a diffusion model, we want to use real images. We want to noise them, and we want to learn the denoiser. Once we learn this model, what we will release is just a model that takes random noise, and it's going to give you an image. And that image will look like something close to your training data. And that was the intent, right? So mathematically, all this turns out to be like you're trying to learn the distribution of the data, so you want to learn the best distribution, and there's some math involved in here. Effectively, that's equivalent to saying the black arrows are going forward. I'm going to design that, adding noise the right way. The green arrows are what go backward. I'm going to emulate the forward in the backward. And you can do that if you write out all the probabilities. And the way to do that is there's the forward arrows induce reverse arrows, okay? Provided you know the training data. So during training, you know this. But once you've done training and you've released the model, you don't have any training data. You have to start from scratch, from noise. So there are two expressions in here. If somebody's interested, you can go back and look at all this stuff. It's basically emulating what the diffusion model will do in practice to what is actually happening in the training setup. So you can do all of this, and all the math tells you is that you add noise in the forward process. That's this noise epsilon. You're learning a model epsilon theta. Theta is the deep neural network parameters, for example. And this theta is continuously updated during training to learn this noise that you keep adding in every step. Okay? So in practice, the algorithms of diffusion have training and then sampling. During training, you're going to add noise, and then you're going to learn how to learn that noise itself. You're going to predict that noise. The entire diffusion model is about predicting noise. Once you've learned that really well, you do this many, many times over lots of data, you release the model, and you can sample from this model. When you sample from this model, you start from very noisy image. And you're going to denoise this image. That means you're taking a trajectory in space like you did in diffusion. You're going to, it's like watching a movie in reverse, right? That's what sampling does. It starts from the completely diffuse state and takes a trajectory back to the drop of ink, which is closest to what was originally done. All right? So this is how it's done in practice. And in practice, it's implemented with what's called a U-net, a U-shaped network, where this first part of it is taking your image and encoding it down to a low-dimensional latent space, and the second part of it is decoding it back up. This is the entire architecture, and this architecture learns at every time step to denoise a noisy image. And so you train it, and then you sample from it. All right? In practice, now that we use generative AI, we don't just have the AI tell us something or show an image. We prompt AI to do what we want, right? So you may want images of people with eyeglasses, of an astronaut on a horse, et cetera, et cetera. So there's a lot of, there's text prompts, so there could be a class prompt like I want bags, I want this, I want that. So how do you make sure the diffusion model does this? So again, there's a little mathematics. The whole point is you can take existing models, don't worry about it, you can take existing models, but you could train them conditioned on some labels you have in your data. So it also learns the labels, so it learns images from those labels and generates something from that class. All right? And you have to guide these models, and guidance can affect how you learn. And this is an important point I want to make here. Most of the time we have a lot of data. For example, if you're in the healthcare setting, you may have cancer data. You may have stage 0, which means no cancer, stage 1, stage 2, stage 3. And oftentimes, if it's a very difficult form of cancer, you may not have enough stage 3 because maybe not too many patients survive. And if you wanted to generate data from these models because you really want to train them and learn new molecules, you need some of these images to do other things, other research. If you don't have enough images, you're not going to learn well. And that's sort of what is indicated here. When you do these conditional models, you're guiding it. The guidance determines how much you go into the class you want or how broad you remain. Now, if you have a class with very few samples, diffusion models and most neural networks, in fact, don't learn well. They don't have enough samples to learn well. They end up learning more features from the other classes. So can we fix this? So this is the topic I'm going to talk about. I don't know how much time I really have. Okay, great. All right. So what I want to talk about mostly is a little bit more practice than the broad theory of diffusion that you heard from me. We're going to talk about what is called encoder entanglement, and I'll tell you what that is in a moment. But let's start with long-tailed. All right. So we're looking at data that have labels on them, and we want to generate images from a large data set that has, say, images of dogs, birds, rhinoceros, eagles. But the number of rhinoceros and eagles are far smaller, the number of images, relative to, say, dogs and birds. Now, it's very well known that diffusion models, you train with the best algorithms that I just mentioned, simply will not generate enough authentic rhinoceri. They will look like some other things. They will look actually more, they can look like dogs, they may even look like birds sometimes. Because what happens is when you have a lot of data, the neural network models will learn the features of those images really well. And they project those features also to the classes where you don't have enough data. How can we fix this? All right? So you get very poor fidelity and diversity for the tail classes, and this is what we want to fix. And this is neither fair from a social goodness point of view, nor is it valuable if you really want to, say, search for rare events, and those are few images. You want to look at the stage 3 cancer, and you don't have enough data, and you want to generate them, for example. All right? So here's an example of the MNIST data set. The MNIST data set is a digits data set. It's black and white. There are digits written on it. And we artificially created a long tail version of it. That means there are lots of zeros and very few nines. So if you now ask this model to generate class 8, and you take a moment to look at class 8, I don't know, you get 6s, you get 7s, you get some even zeros, right? Doesn't look like a very good class 8. Just turn it off. I'm so sorry. Yeah. So then here's another example. This is the ImageNet dataset. The ImageNet dataset was created to train a lot of image models. You can get a long tail version of it. Somebody helped us do this in the universe. They took the ImageNet 2012 dataset, and it has 1,000 classes. And they just, when they do a long tail, basically these classes are arranged in alphabetical order. They literally keep the first class as it is, and then just put an exponential function. So the last class in alphabetical order will have very few samples. Okay, so on the top are generated images for a tail class, which is the Espresso class, which has 55 samples during training. On the bottom is the Jack-O-Lantern class, which had 28 samples during training. I think you would agree with me as some of the Espresso and Jack-O-Lanterns don't look so good. Keep this image in your head, because I'm going to show you really good images a bit later. All right, how do we fix this? So now, so this is what I was talking about. How do you artificially generate long tail imbalance? You just control the number of samples you have in these classes as you go along. All right, and we did it for a variety of data sets. We're not the first to look at it. Other people have looked at it, and they've observed that, hey, when you have more data in the head classes, why don't we use the head classes to guide the tail class? Leads to mode interpolation, sometimes also mode collapse. And all of these methods, they do well, but not well enough. And they work in what I call the ambient space, in the data space. So what we started thinking about is, hey, you use a UNet architecture. Is there something you can look at in the latent space, in the very bottleneck layer of the UNet? Remember, it's a U. You go down in size from your ambient image to a low-dimensional representation, and you go back up. Let's look at that low-dimensional representation. Typically, that should capture the features of an image, and therefore of a class. And when we looked at it, and this is on the left, is a balanced 10-class data set, which is the CFAR10 data set. On the right is the same data set with an imbalance. The A letter has the most, and I think the T, truck, has the fewest. And when you do a 2D visualization of this latent representation, you see that when you have imbalance for these rare classes, it literally, the features just sit on the features of the head classes. So you're only learning mostly the features of the head classes. You're not learning enough of the others. And it's just not enough samples to separate them. All right? So what we thought of was, could we, in that latent space, try to move these samples apart a little bit per class? So allow these classes, they may have very few samples, but guide them to sit in their own space, not to overlap with the majority classes. So what we did was we used contrastive learning or contrastive losses to do this. So what we call it is contrastive regularization for aligning of latents, because we're working the latent space, Coral. Got to have a name, right? All right. So effectively what Coral does is this. It has your standard diffusion. So here are your training data. And right in the middle there on the top is your UNet architecture. And UNet has its, we have our standard diffusion loss, LDIF. I'm going to take the latent vector, and I'm going to put it through another simple layer. All right? What we call a projection head. And you get, and you apply a loss on this latent representation. You combine the two losses and you train the model. So your standard diffusion is still, it has class prompts in it, and it's separating things. Whereas your projection head and the supervised loss that I use there, contrastive loss, let me tell you what that is in a moment, is allowing you to separate things. All right? So that's what I've written here. The UNet output is used for diffusion loss. A projection head is used for the contrastive loss. All right? Okay, so let's for a moment stare at these two. I showed you the original loss at the very top. You're denoising at every stage. All right? That's sort of working in the ambient space. But now the contrastive loss works in the latent space. And what it's doing is it's like an attractor system. If you are in a particular class, it's going to attract all the other latents in your class towards you and repel the latents from the other classes away from you. So it's sort of forcing people to go into their little manifolds. Okay? And it works really well. And of course, you don't want to do it with the same energy from the very start of the noisy image. At the very beginning, remember, when you're sampling, it's all noisy. You want to do it closer to the true image. And so that the SUPCON is the supervised contrastive loss, and the scale factor in front of it tells you how you increase its amount as you get closer to the true image. All right? So this is what we do, and how does Coral work? Effectively, the argument for having an additional layer is as follows. You've got to keep your diffusions UNet to do the things it does. Adding this projection head allows you to guide further. So we're doing two separate things in the bottleneck layer. All right? Okay, so let's go back to the same CIFAR 10. Balanced is on the left. Standard DDPM, as it's called, which is standard diffusion, is in the middle, and I already showed that to you. When I apply Coral, I think it pushes it out quite effectively. There can be other side effects to this, but it pushes it out nicely. And it collects the things that are similar together. All right? So it reduces this overlap by encouraging latent class separation. Let's look at our, so does it improve image quality, right? Maybe this is not a good thing, especially for tail classes. So the right way to compare things, at least the current way to compare things, is some kinds of metrics called Frechet inception distance. What it does is it takes that same bottleneck layer, looks at those features as Gaussian, and compares the real with the generated data. And you can also take your images and you can compare it against a classifier. And you can also look at your generated data and see how close they are to the real data. So that gives you Frechet, inception, and recall. All right? So on all of these metrics, for all the data sets I mentioned, we do well. What does that mean? That means it's good by these accepted norms. But let's look at, I want to actually take a moment to talk about two things. How does it do per class? That's really important. Now, for the CIFAR 10 data set, since a balanced version of it exists, we have enough real data that we can apply FID, and you can do it per class. And you see a real improvement for the tail classes when you do this. All right? I mean, in general, the tail classes seem to have a higher FID than the head classes, but it's still improved relative to the state of the art. I mean, you've got to look within that set of 4. All right, but my favorite way to do this is through visual inspection. So in the CIFAR 100, which has 100 classes, the tulips class is a small class because of this long-tailed effect. And while I don't have the original data, take it from me that Coral actually captures a variety of backgrounds better than the largely green things that you see from the state of the art. The green things are driven a little bit more by either the model learns this green background in other head classes, and so it's driven by that, or it's just limited in what it learns relative to state of the art. But let's go back to Espresso. I'll come back to this in a moment. Let's go back to Espresso and Jack-o'-lantern. Okay? So on the left is we don't do anything. We just run standard diffusion on a long-tail data set. There's the Jack-o'-lantern generated images on the top and Espresso on the bottom. Mostly okay, but still some of them do not look good. Now I draw your attention to the right. I think they look really good. I mean, we should ask the questions about memorization and so on. It's something we're looking at, but I think they look far more authentic. In other words, the model, having this guidance in the latent space, is being forced to learn the representations of these tail classes. We also did this on the Celeb A data set where you can take celebrities and you can use their hair color as a way to do things. And this is the state of the art on the left, and that's ours, the new state of the art. And you can certainly see that This model doesn't even get bald people correctly. It doesn't get hair color correctly. We end up doing it better. Okay? And that Celebay data set was inherently very imbalanced. We had the most blonde people and then bald and then the rest, right? Okay, so it's sort of, I'm done. There are bigger challenges. Most of the time you want to have prompts where you have text, and you want to look at text to image models. For example, in that cancer data set, you want to ask, can you give me a stage 3 image, and so on. But text to image models also have challenges with underrepresented prompts or classes. Somewhat harder in the language setting to talk about underrepresented. This is something we're trying to quantify more precisely. In the medical data set arena, it's a little bit easier for us to do, so that's what we're focused on. And I'm going to stop there and tell you that we presented a new way to generate better images using diffusion models for data sets that have inherent imbalances across classes. And Coral does really well, and it does so by using latent representation.